Okay, so as promised, today's lecture is mostly going to be about this tool called Uppaal, which is the model checking tool. And by now, you should all know what model checking is. This is the last tail end of our second module. We had to skip 2 lectures because of my travel, so we are, I think, 1 lecture behind my original schedule. But there's only 1 more lecture remaining after today's lecture. So today I'm going to walk you through, and I encourage you to follow along with me this Uppaal small tutorial. And if you are able to follow along, then in the final lecture of this module, I'm actually going to show you the heart model and the pacemaker model in Uppaal. And then we'll verify some properties. But that lecture is going to be dense, and it will only make sense if you first understand what Uppaal is and get used to, just like you have learned state flow and Simulink. This is the actual domain tool that we will learn in this module. It's similar to how we spent some time learning Energy Plus in the first module. We didn't go that deep into Energy Plus as we would into Uppaal, though. So this is sort of where we wrapped up our previous discussion. I'm just presenting this slide sort of out of context, but the idea was we discussed how you can construct a Behl automaton, which is the transition system representation of a LTL formula. And to do model checking, we actually want to first construct the Behl automaton of the complement of the formula, right? So we want this transition system to accept traces which violate phi, or our LTL expression. And then we can compose our transition system and this B of not phi together into what is called the product automaton. And then checking whether the transition system satisfies phi or not is as simple as detecting whether there's a loop in our product or composed system which visits the accepting state of this system infinitely often. Right, so we spent all this time so that you have a sort of understanding and also appreciation for what Uppaal does very, very efficiently. So this is where everything comes together. We have discussed what transition systems or a formal mathematical object is. We have discussed how to express queries in LTL. Those are the 2 inputs to our model checker. And then it will automatically tell you and exhaustively tell you whether or not our transition system satisfies some LTL expression. And if not, it will present to you at least 1 counterexample where that transition LTL formula is violated. And it'll present the counterexample in form of a trace, which we all know what it is. So just 2 things before we jump into the tutorial. I want to introduce 1 notation which is specific to Uppaal. So far we have seen how the square is a symbol for globally or always. That's what you submitted in your assignment today. There's another notation which Uppaal model checker uses, and this is this notation which is represented by the capital letter A. And what this tells you is that when I have a LTL formula and I precede that formula with the symbol capital A, then I want that formula to be true for all traces of my model, which is the definition of what we have also studied in model checking, right? A transition system satisfies a formula if all traces satisfy the formula. But in Uppaal, we can be explicitly intentional about telling the model checker that give me a counterexample or tell me yes or no by looking at all possible traces, and we denote that by using the letter A. So visually that would mean these are some thought visualizations of what traces look like. I know it doesn't make much sense what these look like, but what I'm trying to depict here is that from the initial state, your model has many different traces possible. And so when we want to verify some property phi in this case, which we want always phi to be true, then prefixing that by the capital A, I want it to be true for each possible trace of my model, right? Similarly, I can say eventually phi to be true, which would look like at some point in this trace, eventually phi is true. But by prefixing that with A, I want that to be true for all traces. So why do we need this operator? Because there's another operator called E, which says there exists at least 1 path where the formula is true, which is a deviation from our regular model checking sort of definition. So I can ask the model checker that does my model satisfy a LTL formula phi But if I say E followed by that LTL formula, I'm asking the model checker, is there at least one path? It may be true that all paths don't satisfy phi, but I just need to know, is there one path which satisfies phi? Why is that useful? We can at least say, is there one path where something bad happens? We know that the model may not satisfy always something bad happens, but I want to investigate, is there one path in my model where something bad can happen? That's where this sort of a notation is useful. So we will use this in our Uppaal tutorial. So I just wanted to introduce that because I'm going to use that today itself. So with that being said, I would say just fire up Uppaal already. I'll give you some time to launch it. I hope you were able to install it. I think there were some problems maybe with Java or something, but we can revisit those later. So this is what the Uppaal model checking tool looks like. And depending upon your operating system, it may look like it may have many different tabs, but at the very least you must have something called the editor and then simulator and then verifier. I know that on the Mac OS these tabs are situated in the middle, at least in the version that I have, but you may have additional or fewer, but these three should be present. This is what we will basically need to do our tutorial. So what is Uppaal? It's essentially a way for us to describe our transition system in form of this visual flow diagram with guard conditions and synchronizations and actions and resets. And then we can simulate this system, which you already did in sort of Simulink. And finally, we can input some query in the verifier and ask whether my system satisfies that query. And I can use the for all paths or at least one path. So let's build our first transition system to just get a feel for what am I looking at, where is what, which function resides where. So this is your main editor window, and on the left is this panel which tells you about your current project. So we won't touch this for our simple example. Here is the main sort of taskbar that you will use to build your transition system. So I'm hovering my mouse over this big bold arrow which says selection tool. This is the default selection when you launch Uppaal. So if I have to add another state, I will say add location state, same thing, we've gone over that. And then I can click anywhere and Uppaal will add a location for me. I can keep clicking and add as many locations as I want, but for this example I don't want too many locations, so let me just delete all of them. To delete them, you have to notice I had to select the selection tool again to get out of this add location mode. Okay, so you can drag and drop them any way you like. I think if you click on this button, it will also fit it to view. So that's useful. So how do you interact with these locations? If you double click on this location, some pop-up will come up and you can name this location. So let's call it start, and it's already selected as the initial location. So maybe one clarification here is the concentric circle, don't get confused, right? So far we have said if you see this double circle notation, this is like an accepted state in the Buki automaton. In my lectures I emphasize that. This is not what Uppaal uses it for, right? Uppaal's notation, instead of this dangling arrow, is that a double concentric state or a location is just the initial state. Okay, so don't be confused by that. So here is my location start, and I can call this location end. I don't have to checkbox any of these options. It's just an ordinary location. Then I can add a transition going to this add edge functionality. So you simply click on your source and click on your destination, and a transition is added. So one thing you have to get used to is whatever function you are currently in, it is getting highlighted on the top. So to manipulate or double click, you have to be always in the selection tool. Okay, otherwise it'll keep on trying to add an edge or keep on trying to add a location. One again useful tip is if you simply hover your mouse over the label of the state, you can even move that around to make it more clean. And this simple example, it doesn't matter, but later on you'll see if you have a lot of locations, it can get messy. So that's it. This is my first automaton. It's not something useful. It's not doing anything. There's no guard conditions. or any sort of inputs or resets defined, but it is a transition system by our definition. So before I tell you what to do next, one quick overview of this left-hand panel is, we've seen in Simulink that we created a node automaton template. And then we could patch it anywhere, and you did this homework exercise where you could do npn or npn. So you could take that node automaton structure from ERP to RRP to REST and just change the parameters of that basic structure, and it would be a different transition system altogether for a different functionality. So you're already familiar with this notion of templating, right? That was my template I provided to you in the Simulink model library. Similarly, what I have drawn right now is a template. And just like in C++ or any object-oriented programming, you can create the class or a template, and then you can instantiate objects of that class or that template as many times as you want. So that's why Uppaal considers this transition system as a template. It's a very basic system, so we can't do much. But to convince you that it is indeed a template, if you go to systems declaration, I apologize if this text is too much on the projector, is too tiny. But what you should see is we are creating an object called process, which is an instance of the template that you just created. And then you create a system with just that object. Okay, so this is a very basic example, but it will become clear later. So we are done. This is my basic example. Let's look at the simulator tab. So we click on simulator. It will ask you, do you want to upload this to the server? Just click yes. Server is not something running in the cloud. It's on your machine, but it's just bringing that template or creating the system, right? So the system is called process. And let me bring this, drag this window up a little bit as well. I can again make this a little bit bigger. So our system is not doing much, but I want to take this opportunity to at least tell you how to view all these different tabs that you see on the simulation window of the model checker. So on the left-hand side is what we can call or consider as our control tab or control panel. So you can see that what is highlighted here is that there's only one transition you can take at the moment, and it's also highlighted in red. You can go from start to end. That's the only thing, in fact, you can do at the moment. So if there's more than one transitions available, a list of them will be provided, and you can choose what action to take next. Okay, so right now we can only take one action, so let us click on next. And so you can see our state has changed from start to end, highlighted by the red color in this case. We can also see the trace of this simulation, or the path rather, because we are just looking at which locations we are visiting from start to end. And now there's no more enabled transitions, because indeed in my transition system I didn't specify any way to go back to start. So we are in a deadlock, and Uppaal recognizes that and says that there's no enabled transitions to take from this point onwards. You can even say the simulation traces, we went from start, we took a transition in the process automaton, and then we visited end. Okay, good so far? Let me know if you want me to slow down so you can actually follow along. So this automaton, like I said, isn't doing anything useful, but still we can check some properties of this very basic automaton. So for that, we go to the third tab called verifier. And in the verifier, you have options on the right-hand side where you can insert a LTL formula or remove a formula. So let's try to insert one query, and the query is, I want to say that there exists a path, so E, such that eventually, which is this diamond symbol, we can reach the state, the location, process, and end. Okay, this is my query. So Uppaal, as I was typing this query, I can also, and I encourage you to do that as well. When you type a query, it's a good habit to translate that in plain English and type that as the comment. So that's why the comment field exists, because the queries can become very complicated, and that will happen in your heart model. So this is a good habit that even though this is a very simple query, we are going to add a comment to this query. Is the text too small? Let me try to see if I can fix that. Yeah, okay, so, wow, that's weird because it doesn't show. Yeah, this is what I typed in. Okay, eventually process ends. So in other words, I can say in plain English, the query is, it is possible to reach the location end in the automaton process. That's what this is, because I have said there exists at least one path. So what do you think? Is it true for a simple automaton? Of course it is true, right? So we can go back to verifier and click on check, and you can see the model checker says the property is satisfied. So it's a very basic example, but I wanted to take this example to show you the workflow of how to create a system as a template, how to load it into the simulator and go through some transitions, and eventually input the LTL formula as a query and just hit the check button, as simple as that. Well, let me add another query, right? So I can say the same thing, but instead of E, I want to say always eventually process.end. Right? So here I am asking, let me zoom in again. Here I'm asking for all paths in my automaton is eventually I will reach process.end, the location process.end, right? So this is just an example of using the A operator. So what do you think? Is this satisfied in this model, or should be? Don't cheat by clicking on check. Just tell me what do you think first. Is it possible? There's only one path. So is it possible that for all paths we will be in end? Okay, so I hear a lot of yeses. So let's go ahead and click on check. The property is not satisfied. And I can tell you that the model checker hasn't made a mistake. So can someone try to guess why is the property that for all paths eventually we will reach end is not satisfied in this simple transition system? What could be what could be your intuition? Okay, let me give you a very obvious hint. The first part of the answer begins with the word non. Okay? Non-determinism, that's the only sort of word we have encountered which begins with non. So what is happening is, and this is my chance why I started with this simple example. Unlike Simulink, where when some timer expired and you satisfied the transition guard, you had to transition. There was no non-determinism there. In a transition system, specifically, when you model this in Uppaal, and it's true for transition systems in general, that when you satisfy the guard condition, it only means that the transition is available for you to take. It does not mean that you have to take it. So there's already non-determinism here. So I can remain in start forever and never visit end, and that's allowed, even though at all points the transition is available. So indeed, it is true that there exists some path where you will visit end eventually. So E of eventually process.end was satisfied, but it is not true that always you will have to visit process.end because of non-determinism, right? So previously we have seen an example where non-determinism was related to how the inputs were affecting the transition system, right? You had a transition on Q and Q or something like that. Here I'm telling you that really at the heart of non-determinism is the idea that when a transition guard is satisfied, then that transition is just available for you to take place. You can use it or you cannot use it. We will explore both possibilities. So it's not true that all the paths satisfy the property that you will eventually reach process.end. Okay, questions on this? Because this is sort of breaking our previous notion of what non-determinism was. Any questions on why this doesn't satisfy? Yes? There is a self loop, but even a self loop is a transition that you can take to revisit your own state, correct? What I'm telling you is for all transitions, what is a transition, right? So it's a transition, and then there's some set which tells you when you can take that transition, right? So in Simulink, there was some condition on timer expiring, or you get another reset function or some signal from the atria, and then there was no option. When you satisfied the condition to the transition, you had to take it. There was no other way for Simulink to do anything else. In Uppaal and in transition systems, even the fact that you have satisfied the criteria just tells you or allows you to take the transition. But it is also allowed to not take it. And I'll explain to you later at the end of this lecture how we solve this problem. What we can do to actually force our system to take a transition, when we want to sort of simulate some property of a real system itself. All right, so that's a very, very basic introduction to what Uppaal is, but we will appreciate it more after we look at a slightly complex system. So let's go ahead and create a new system. It will ask you if you want to save it. You can if you want. I don't really care, so don't save. And we have a new system, okay? So now I'm going to refer to an example from this Uppaal small tutorial, which I think is also downloaded when you download Uppaal. It should be in some example folder. But we'll build the system together. So let me just quickly pull up the example. So our example is this algorithm of mutual exclusion. Okay, has someone encountered mutual exclusion in some programming class before, or theory of computation or other stuff? Okay, not many, so let me go through it. So mutual exclusion is a very, very common algorithm, and at the heart of it is the idea if you have a shared resource and two entities are competing for that resource, then we want to ensure that both of them don't access the resource at the same time. So what are examples? Examples are we want to read and write to a shared memory space in a computer. We want to transmit packets over the shared bandwidth in a wireless channel. So there's many, many examples, and this Peterson's Mutex or mutual exclusion algorithm is one of the most famous and basic algorithms which ensures that. So let's take a look at what is going on. We have two processes, and both these processes want, say, processor time to execute some part of their code. So what mutual exclusion tells you is it's a very polite protocol. Okay, so here's the idea. Let's say I am one process, and let's say Sandesh is another process. So I want to execute. What I will say first is I will issue a request. If I'm process one, I issue a request that I want to execute. So I set my request line or request flag to 1. But since this is a very polite protocol, I say, even though I want to execute, I actually want it to be your turn to execute first. Okay, so if you were pending an execution, go ahead and finish it, and then I can do my stuff. So it's a very polite protocol in that sense. And then we say we can wait while it is not my turn, so while turn is not equal to 1, and if the request of the other process is not 0. So that means the other process actually also wants to execute. So I'll wait as long as someone else wants to execute and it is not my turn. And the only way to break out of this is, both of these conditions have to be satisfied. So it should be your turn, and the other process should not be. The other process could be waiting as well. But who can set turn? It's the other process. You cannot control your own turn. The other process will tell you whether or not it is your turn because of this politeness. So as long as this condition is true, you keep waiting in this while loop. When you break out of it, you execute whatever we can call your job. It could be a printing or wireless transmission or just executing on a processor. And after you are done, you set your request line to 0 to indicate that you are done. And this can repeat as often, as many times as you want. And so process 2 is the exact clone of process 1, except that it's using its own turn and request variables accordingly to ensure there is this politeness mechanism. Okay, so it's a bit symmetrical protocol, and this is also an example to show you how, in this case, we can go from a code to or a pseudocode into a transition system. So how do you even think about modeling all of this protocol as a transition system? Well, here is one example. So here I can say I have two processes, process 1 and process 2. Let me actually zoom in first, because I can divide the exact same code into some states on my own, right? So I can say that you are first in the state idle because you are not requesting anything. Then you go into state that I want access to the resource. So you set your request flag to go to that state. Over there, you transition to a state called wait, while the other process is also figuring out what it has to do. And finally, you go to your state called critical section, where you execute your code and reset your flags. And the second process does the same thing. So we can depict that as the following transition system. So let's actually take some time to make sure we understand what this is, right? So on the left is the process 1, and on the right is process 2. So process 1 is first in the idle initial state. Then it goes to the state of I want access by setting the request flag to be equal to 1, or the request variable in this case. When you are in want, you also say, well, I need access, but let me wait by setting the turn equal to the ID of the other process. So this is the politeness part, right? So I'm going to wait for my turn by setting turn equals to process 2. I'm going to be in turn, and here's one thing that you may find counterintuitive, that in our code there was an AND condition, and I'm modeling that as two different branches. So it almost seems like it's OR, but let me convince you that if one of them is true, the other one is also automatically true. So you can just represent it as the following two conditions to differentiate which one is actually causing the transition to take place, but they are functionally the same. So I can get out of my wait state as long as it's my turn, and if the other process isn't requesting anything. Both conditions are true. Then in the critical section, I can execute whatever. And finally, when I return back to idle, I reset my request flag. And process 2 does the same thing. So are there any questions on what the protocol is trying to do? So before we go further, what would be an interesting property to check if we wanted to execute this? The whole idea, the whole purpose of existence of this protocol is to ensure that process 1 and process 2 cannot enter their critical sections at the same time. So we would formulate that as a LTL formula and verify whether it is true for all cases or there exists a counterexample, so on and so forth. The other thing that this example is a really good example for is this protocol is symmetric. So process 1 and process 2, they are essentially the same automaton. It's just a difference of variable assignments which distinguishes them. So it very naturally lends itself to this idea of creating a single template, and you can spawn as many processes as you want using that template. Okay, so the next thing we will do is to build this template in Uppaal. So let's go back into Uppaal again. And I'm in a new project, so all my history is irrelevant. So let me first create some locations. I'm going to create my 3 more locations beside the initial state. Then I can create some, or let me name these locations first. So in order to name them, I have to go back to the selection tool. So I'm going to name this location as idle. Let's name this one as want, followed by wait. And finally, we can just call this the critical section. And let me actually move these labels aside so that I have some space for drawing the transitions. Okay, so this is our basic example. Let's create some transitions. So you can go from idle to want. You can go from want to wait. From wait, you can go to the critical section in 2 ways. I just, you can go, by the way, to make this edge bend, if you haven't figured it out, you just have to click in the middle. And then you can go back from the critical section to idle. Okay, so this visually looks like what each of the transition systems look like. but the trick is now in inputting this guard conditions and updates, right? So if I double click on the edge, it opens another sort of dialog box for me to update or add information about what controls this transition. Just like if I double click on the location, it opens its own dialog box. So to go from idle to want, I want to issue an update by saying that let's set a variable called request underscore self equal to 1. Okay, so make sure that there are many options, right? There's an option called guard, sync, and update, and we will go through all of them. Right now, I'm using an update. I want to reset a variable, and therefore that's in the update box, and it should appear as this blue, guard condition in your transition system. So if I'm on idle, I want to request my own self to be equal to 1. That makes sense. Then I go to want. To go from want to wait, I want to have another update. Actually, I want to have a guard condition, not an update. So here I want to say, sorry, I think I'm making a mistake. It should be an update because we are setting our variable turn. So follow along with me. I'll explain what I'm writing. So you can say turn colon equals, which is the symbol for assignment. And in parentheses, you can say turn colon equals me double equals 1. I'll just explain what this is. Question mark 2 colon 1. And I'll highlight it too so that it's visible. This is what I have typed in. So turn colon equals some logical condition me double equals 1, question mark 2 colon 1. So what is this again? This is the ternary operator in programming. So the way to read this is, I haven't defined what me is right now, but if the value of me is 1, then the value of turn is what is followed after the question mark, which is 2. So if I am process 1, I will say turn equals 2, else turn equals 1. This is how you read it. Okay. So this should appear as so. Now to get out of wait, we actually need a guard condition. So this time when you click on the upper transition from wait to critical section, we go into the guard box, not the update box. And a guard condition is simply turn equals me, which is a variable that we will initialize. And the guard condition at the bottom is request, this time other, double equals 0. Okay, so this is my template notation for trying to create a general template where I can instantiate the variable me, I can instantiate request self, I can instantiate request other. And then finally, to go back to idle, this time it's going to be an update, and the update is request self is 0. So you have finished your execution, so now you can just reset your request flag. Okay, so take some time to make sure your transition system looks like this. So while you do that, let me quickly tell you what we have done. This is an update to go from idle to want. This is also an update with the ternary operator. Then we go to wait. These are not updates in green. They are guard conditions. One guard condition is turn double equals me. The other is request of the other process is 0. And to get out of your critical section, you set your flag to 0. So this is our template. And in fact, we can go to this window over here on the top, which says template, and we can call it Mutex. Okay, let's name our template something. So I'm calling it Mutex right here. So I'm not done though, because Uppaal doesn't know yet what is me, what is turn, what is request self, what is other, and things like that. So I have to give some, so we have to declare these parameters or arguments to our template Mutex, so that when you create the instance of this Mutex, you can provide values to these arguments. So that happens in this parameters tab right here. and I'm going to type it along and speak it so as you can follow along, and then I'll zoom into it because the font is too small. First, let's declare what me is. I would say me is a constant, const, that's the abbreviation for that. It's the constant integer which can only take two values, 1 and 2, which are the process IDs, and so that's its definition. So constant integer 1 and 2, that's me. We have another definition for this time an integer which can take values 0 and 1, and the argument is this variable request self. So you have to have the ampersand before request. Okay, so request self is a variable that you have to provide a value for, and whatever, the request self is a variable which will accept another variable as its argument, and that variable can only take a value 0 and 1, right? So if you look carefully, request self is trying to model this part, right? So here we say we have a variable request 1 and request 2. Now I have just declared an argument request self that you can pass request 1 and request 2 to. That's what we are trying to do. Okay, so let me just type it out. We do the same thing for request other. So integer which can take a value between 0 and 1 in square brackets, and ampersand request underscore other. So just to make sure, this is what you have to type in the parameters.template. Okay, now let's go to system declarations. Oh, sorry. Yeah. So constant integer which values 1 and 2 is me, comma, another integer with 0 and 1, request self, which is the variable or the argument name. So this and implies that it will accept another variable as an input. And then finally the same thing as request self, but with request other. Okay. So having sort of made the template, let's go to systems declaration, which will have this default example over here. So here I want to actually create my processes P1 and P2. So I'm going to say P1 is an object of the type Mutex, which is the template I created. The value of me for P1 is 1. The value of request self for P1 is just req1, just as in the PDF, and the value of request other is req2. Okay, and a semicolon is required for this to compile. So P1 is Mutex with these arguments, and similarly we can say P2 will be another instance of Mutex with 2, request 2, request 1. So we've just created two objects of the type Mutex by passing it some values and these three values correspond exactly to the three parameters of me, request self, and request other. So let's also edit our system, because now my system is nothing but P1, P2. This is my system. I have objects of type Mutex, and my system has both these objects inside it. There's just one last piece of information missing, which is our Uppaal doesn't know yet what is this variable turn and me. We haven't really defined, what is this variable turn, and then what are these variables request 1 and request 2. So just like you had a system declaration, there's a dedicated field called declarations, which should, if I had to rename it, I would have called it global variables. That's the way to understand it. So we need to define turn as a global variable because both the processes require access to the turn or the value of the turn. Similarly, both the processes require access to the value of request 1 and request 2. So we go into declarations, and finally we can say that turn, or let's first define the request ones. We have an integer which can take the value between 0 and 1. And this integer is defined as request 1 and request 2. So both of these sort of integers can take a value between 0 and 1. This is their global declaration. And finally, we also have another integer which can take a value 1 and 2, and this integer is called turn. Okay, and let me do this thing again so it's visible. This is what we have to declare globally. Why globally? Because it's shared. That's the only way, and this is very similar to how other programming languages and Symbolink also works. Now we are really done. Okay, now we have a global declaration. We have a template which can accept these arguments that we have defined here. This template is called Mutex. I'm creating objects P1 and P2 of the type Mutex with the correct instantiation of the arguments, and finally a system. So while it may be, you may be sort of encouraged to click on simulator next, one very good exercise is if you actually go into your editor, on the bottom is this hidden panel, which shouldn't display anything. The reason this exists is that it's a good idea after having declared all these things to go to tools and click on check syntax. And nothing should appear if you typed everything correctly. So let me actually break this down to show you how it works. If I go to turn and if I add this space between my colon and equals, which is not a valid operator, and now say check syntax, it tells me that there's some error, syntax error, unexpected colon. Okay, so this is just a good sanity check to ensure that your system has no errors before you try to simulate it. So let's jump into the simulator now and click yes. So here we go. Uppaal has automatically created a system now with P1 and P2, right? So we have two automatons, P1 and P2, and notice that it has substituted the variables according to what we passed down in the arguments. So request self has become REQ1, and request 2 and turn and so on and so forth. So now it actually is a better model to play with, right? So let's revisit our control panel on the left. Now it shows there are two transitions which are available. P1 can go from idle to want, or P2 can also go from idle to want. It's up to me which trace I want to simulate. So let's just say click next on P1. So when you click next on P1, you went from idle to want idle. So this is sort of showing you the joint trace of both the automatons, which is also being visualized here on this window. So P1 is in want. Let me say you keep going, and so P1 enters the wait state. And look, in the global variable window, turn has become 2 because this expression evaluated to turn equals 2. Okay, so now P1 is waiting. P2 still hasn't even requested anything. So one possible trace is that P2 didn't request anything, so P1 should be able to just execute. Right? So let's go through that. I can select P1 and then next. So P1 executes its critical section. We can do P1 again, and we are back to idle. P2 didn't do anything in this entire story. But this is not that interesting. So let's try to make it interesting. P1 goes to want. So I highlight P1 and click next. Whatever transition is highlighted here is also highlighted in the automaton. So it's easy to visually see what you are trying to go to next. Then P1 goes to wait, and now I want P2 to actually request its execution. So we will select P2 and click next, and look what happens. When P2 requested or went to the want state, P1 cannot make any progress. The only enabled transition is on P2 because of this politeness. Because when P2 requested its line, this condition is false. P1 cannot get out of wait because request 2 is no longer equals to 0. Right? Request 2 is 1 right here. So the only thing that can happen now is P2 will set, being polite, turn equals 1. Okay? So turn is equal to 1, and you can jump out of this waiting state because of this politeness. And so now P1 can execute its critical section and go back to idle. And now P2 can. Since P1 has done its job and request 1 has be set to 0, P2 can now execute as well. Okay, so we built this, and I encourage you, if you followed along, to try and go through this and try to get both of them in the critical section at the same time by playing with which transition occurs when. And you can spend as much time as you want. The whole idea why this protocol is so useful is it should never be the case. Okay? So you can simulate it for a week and still report no counterexamples. But that's not enough. That's similar to submitting in a Simulink model of your heart model and saying that for 10 seconds nothing bad happens, so nothing bad will ever happen. So a better way, and this is where really Uppaal shines, is let's input this requirement of mutual exclusion as a LTL formula and see whether it is true for all paths in this joint P1, P2 transition system. Okay, so we should go to verifier, and here's an example of a query you can type. So let me type it first. For all paths, A, always, so square brackets, it should not be the case, parenthesis, that P1 is in CS, P1.CS, and P2.CS. Okay, so this is the LTL formula, which says that it should never be the case for all paths that P1 and P2 are both in their critical section at the same time. So it better be true, right? Let's check it. Yeah, property is satisfied. I can also say another property, so I can say insert. Another property is, I'll just write it and then someone can help me translate that into English. So E followed by eventually and then P1.CS, right? So can someone translate this into a comment? What is this property? E eventually P1.CS. How would you read this? Yeah. Correct, right? Or a simpler way is that P1 can reach its critical section at least in some path. So what do you think? Is it true or not? Should P1 be able to reach its critical section? Yeah, why not? So let's check it. It is also satisfied. So you can come up with as many properties as you want and keep trying to play with it. So let me show you an actual example where this is a counterexample, and that will also tell you another very important functionality of Uppaal, of how it presents a counterexample. We haven't really seen that. So for that, I'm going to actually go back to my editor in the template, and I'm going to make a very sort of a big change in the protocol by saying request other equals 1. So functionally what I'm doing is I'm saying I'm still polite. I will issue the turn to you, but then I don't care. I'm going to execute regardless, even if you have requested it. So we are breaking the protocol, essentially, on purpose, just to show you what counterexamples look like. So you made this change to the guard function in your template, remember? So here's the beauty of it, right? I don't have to change it in both of my processes because they are just an instantiation of this class. But I won't simply jump back to the verifier. After you edit your model, you have to sort of reload it back into the simulator for it to take place, its effect to take place. So you can see now both request 1 and request 2 are equals 1. We have just flipped the protocol just for the sake of it. And now, here's how you look at a counterexample. First, you go to options. In options, there's a field called diagnostic trace, and you can set that for the time being to some trace. And you can see already, there's a notion of what's the shortest trace or the fastest trace, but right now let's just put some trace. So I've switched diagnostic trace to some, and then I can go back to my verifier, and let's try to check this first property of mutual exclusion again. That in this new Madhur's version of Mutex, which doesn't work, is this true that for all paths, always P1 and P2 will never be in their critical section at the same time? So let's hit check. Yes, property is not satisfied, which we expected. But don't just tell me it's satisfied or not. Show me an example where it is not satisfied. So since we turned diagnostic trace on, we can go back to the simulator, and it has already loaded a trace for me, where at the end of the trace, you can see both P1 and P2 are in the critical section. So I can go back to the first part of this trace and just hit replay, and we will walk through all these transitions, which is a counterexample to my LTL, which is why the property was not satisfied. And you can play with, if that was too fast for you, you can make it take more time to look at actually how these transitions take place. Okay, everybody. I hope everybody likes Uppaal after this, because it's doing all your job for you. You just give it the correct model, give it the LTL formula. It'll produce a trace or tell you exhaustively and automatically if it is satisfied. And it's up to you how rigorous you want it, right? If you wanted all paths to satisfy, just put an A. If you want at least one path, put an E. So questions on this before we go on to the last example for the day, which is actually pretty straightforward. Any questions? Yes. It's doing exactly what we studied in the last lecture.
Okay.
So the LTL formula that you specify underneath the hood is getting converted into a transition system. It's composing them together and finding this cycle. So it's doing it. That's why we spend time on that, right? So good question. Not in this tool, but there are tools which can actually show you what is the composed transition system as well. And in Uppaal, not so much. I think in the commercial version maybe, but I can't be sure. This is a free academic version, so this just tells you the answer. But there are tools which can help you visualize why the cycle existed or things like that. Okay? Yeah. Any other questions? Impressed? Not impressed? Don't care? Okay, let's do the last example, and then there's one more concept which we haven't explored that you will hopefully enjoy. So once again, I'm not going to save the system, but you can if you want. Okay, so we are back to blank canvas, and so this time I am going to be a little bit faster because I want to get to the interesting part first, but you can still follow along, right? So I'm going to draw two templates in this case. So right now we've only seen an example of one template, multiple objects, but there can be more than one template as well. So let's do that, okay? So my first template, I'm just going to call it simply P1. That's a good name. This initial state, I'm going to call it loop. Okay, so this is my state. As the name implies, I want to go to my edge selection and just draw a big self loop. Oh. I don't know if it actually connected or not, so probably did, but let me draw a cleaner one. Okay, so this is a simple self loop. In this loop, I want on the edge, I want a guard condition which says x greater than or equal to 2. That's my guard condition. And I also want to issue a message or a synchronization message called reset. And the way to tell Uppaal whether you are issuing a message or listening to, similar to sort of Simulink, when you have an exclamation mark, it means I want to issue this message. And if you have a question mark, it means I want to listen to a message. So this is what I've done for my edge, right? X equals greater than 2. I haven't defined what x is, but it's a clock. And then synchronization on reset. Okay, so this is what my system should look like. And it's very useful to move things to the correct locations. Okay, that's my P1. Not much going on yet. Now I'm going to create another template. So to do that, you go to Edit, and you can insert template. This is different from inserting a whole new Uppaal project, so don't make that mistake. So go to edit and insert template, and we have a new canvas while P1 already exists. And so here I'm going to call it an observer. So let me just abbreviate that by OBS. Right, this is my observer, and you will see what this does. Let's first add one more location in observer. That's all we need. And I'm going to add some, let's name them first. So this first one is just idle. So you're not doing much when you are here. And here's a catch. In the second location, when you double click, we can call it, say, taken or received. You can choose whatever. The catch is you have to check box the committed option. I'll tell you what it does later. Okay. So this is a committed state. It's intuitively shown with this capital C symbol, which is a copyright symbol, but it's committed. So now let's draw a transition between these. And after I label these transitions, many of you will already know what is happening in this system. But let me just draw the transition first. The top transition, I want to have nothing but a synchronization called reset question mark. So I want to listen to the reset message. And that's what's enabling me to go from idle to this state where I've taken the transition. And on the way back, I want to issue an update x : equals 0. Okay? This is what I want to do. So let me just blow this up so everybody is with me. It's a pretty basic automaton with one reset condition on the top one and an update on the bottom. The only weird thing is this committed state, which I haven't explained. Let's very quickly go to our declarations. So we don't need process template. Actually, in this case, you don't need to, our template is already called P1. It doesn't take any arguments. Observer doesn't take any arguments. And I don't really want to create more than one P1. So actually, I can simply say system is just P1 and observer without creating any objects. That's also allowed, which just automatically means that whatever template exists for P1 on observer, just create one object of it without having to create a new name for P1 instance equals P1 parenthesis. That's not required. So what is the last thing remaining after this declaration, which again, I should not be so fast. I should tell you what I have typed. So system P1 and observer is my system declaration. What we haven't told Uppaal is what is X and what is reset. So that's our global variable because they are shared in two sort of templates. So I can simply say clock X and semicolon. So I'm declaring X as a clock. And I say channel, CHAN, reset. Okay, so this is me telling Uppaal what is X and what is reset in these templates. And these are the only things that exist in the template, so we are done. So what should we do next? What should we do next after we have declared stuff? What do we usually do? In the previous example, what did we do? Should we simulate? No, we should not simulate. We should check for syntax errors first. Okay, so options or tools, check syntax, and there's no errors. Now we can jump into our simulator, load these models, and let me make things visible. So this is our system. This is my system. And now when you see both of them side by side, you have some idea of what it's trying to accomplish. Essentially what we have done is we have a process P1 which just loops every time X is greater than equal to 2 and issues a message called reset. And the observer, which is observing or monitoring the process, is triggered or captures that moment when the reset message is issued and resets the clock for the process. Okay, so notice how the reset of the clock is happening in the observer and not in the process itself. Okay, is it clear sort of what the basic framework is? So let's look at our enabled transitions, right? So the Only thing that can happen is already highlighted in red. You could self-loop when x is greater than 2. So let's take that transition. You go to taken, and then there is no guard condition, so this transition can be immediately taken if you want. So let's, this is enabled, so if you go next, then x will be 0 again, and the same thing happens. I just started from loop and idle. This is the Uppaal notation for saying that a message was issued from P1 to observer, shown by this arrow, and you went to loop and taken, and then you are back to loop and idle. Very basic sort of, not much is happening. So let's check some properties of this system, okay? And that's sort of the last thing I want to cover in the tutorial. So let me type it first. I'm typing capital A square brackets observe dot taken imply, not implies, just type imply x greater than equal to 2. So let me zoom in. This is what I have typed. So can someone just give me a comment on what we are trying to check? How would you read this in Uppaal speak? A square brackets observe taken imply x greater than equal to. Anyone? And it should always be this case. Okay, so for all traces, it should always be the case that if you are in the taken location in the observer, that implies that the value of x is greater than or equal to 2, right? So let's look at this picture and let me restate it. It says for all traces, always, if you are in taken, x should be greater than or equal to 2. Right? Because when would you get the reset? When x was greater than or equal to 2. So what do you think? Should this be satisfied for our system? Is it true that when you are in taken, the value of x has to be greater than or equal to 2? It's just a yes or no. If you are, don't hit on check again. Just tell me if you think. Yeah. So I see a lot of nods. So yes. Let's check it if it is satisfied or not. It is satisfied, right? So this is the property at the very bottom. It is satisfied. Indeed, it is the case, which is intuitive because the only way you can go to taken is if you receive a reset. And why would you receive a reset? Only when x is greater than 2. So straightforward. So let's do one more property. This time the property is there exists a path E eventually where the observer is in the idle location and x is greater than 3. That's what I want to check. Okay, so quickly zoom in. Here's what I've typed. There exists a path which is E such that eventually the observer would be idling but x would be greater than 3. So let's take a look at our system again. Is it possible that there exists a path that the observer, which is this automaton, is in the location idle and x is greater than 3? Yes or no? How many say no? Wow, so the others think yes, or? So let me hear from someone who thinks yes. It is possible.
It's possible because we don't have to take that branch in P1 just because x is greater than 2.
Very good. So let's go to verifier and confirm what Aaron said, right? So we are trying to check if it's possible to be in the idle state in the monitor, whereas x has violated sort of your guard condition in the P1 process. And if we say check, yes, the property is satisfied. In fact, I can make this 30,000 and say check, the property is still satisfied. Because once again, when you are in this location loop, x greater than equal to 2 only tells you that you can take this transition. It's enabled now, but it doesn't force you to take it. So there exists a path. We are not asking for all paths. So there exists a path where you would never come out of loop for infinity, no matter what the value of x is. So again, this sort of counterintuitive thing is an example of non-determinism. So let me tell you, how do we fix this? How do I actually force my system to get out and take the transition? One idea is to make the state committed. Committed means if you enter the state, you have to take the transition in the next step. You cannot have the luxury of being non-deterministic. That's why you are committed. The other way is the following. Let me go back to the editor, and in my process loop, I'm going to double click on my location, and there is this box called invariant, and let me type x less than equal to 3 as the invariant for this location, right? So far we've been typing guard conditions and updates mostly for transitions. This time I'm typing an invariant property of my location. What this tells Uppaal is, yes, you can be non-deterministic as long as you don't violate the variant. So when x is equal to 3, you have to go out of loop if this transition is enabled. It's forcing my hand. So if I go back now to first to simulator, to update with the variant, and then to verifier, let me now ask the following, or check the following property, that for all cases, always observer taken implies that x is less than equal to 2 and x is greater than or equal to 2 and x is less than equal to 3. So what this is saying is, for this updated system, you should, whenever you are in the taken location, it implies that x can be anything between 2 and 3. Why is that the case? Why is it between 2 and 3? It has to be above 2 because the only way to go to taken is by receiving the reset signal, and which you will only get when x is greater than 2. But now we say it cannot be 30,000. It has to be less than 3 because it cannot violate the invariant of the process. So indeed, this property will be satisfied. So if I say check, it is satisfied. So I can keep experimenting. Let me, as long as we have the system, let me try another one. There exists a path where eventually the observer is in idle and x is greater than 2. So there exists a path where observer is in idle and x is greater than 2, which means that x was greater than 2 and we didn't take our transition. So yes, there should exist a path because x can be 2.1 to up till 2.999 whatever, and still remain in loop and in idle and not take the transition because it didn't violate the invariant. So let's do a sanity check. Yes, it is satisfied. And now finally, I promise this is the last thing. What I'm going to do is I'm going to remove the invariant and try to incorporate that as the guard condition. So x greater than 2 and x less than equal to 3. Right? I can even do this, where I'm saying you can take this transition when this condition is fulfilled. So for this updated system now, where there is no invariant, but we have a sort of a logical guard condition rather than a single atomic proposition, do you think this system satisfies this property? Can we remain in idle and x still be greater than 3? Is it possible in this system? Can I be in idle when x is greater than 3? Whereas I'm saying that this transition has to be taken between 2 and 3. It is still possible because the invariant is the one which is preventing your non-deterministic behavior, right? So you could put whatever logical condition here. All that is telling you, and I'm repeating this point because this is really at the heart of our heart model, that all this is telling us is when is this transition available. It's not forcing me to take the transition. So indeed, for this updated guard condition, X can be 30,000 and the property is satisfied. You haven't transitioned. The only way to transition is by enforcing an invariant. So why is an invariant such a great tool? Because imagine a heart model in Simulink, you had some very specific value of ERP and RRP. That's unrealistic. Who are we kidding, right? I don't have a specific ERP which is 150 milliseconds. No, everyone has a range of ERP and RRP and default periods of their SA node and AV node and whatever. So this allows you to simulate that behavior, that as long as the ERP clock is within this range, you are allowed to be in ERP. But any time between that range, you are allowed to transition as well. So we are exploring all possibilities. That's why this model checker is so much more powerful than what we did in Simulink, which is the state flow transition system. We can input timers as ranges using variants and guard conditions so that we can transform our original heart model into a model where the timers of the model are ranges rather than single numbers, which is much more similar to how human hearts behave. Okay? And so the last piece of this module is going to be understanding that heart model. Okay? So everything will come back together from what we started on the first day. How do we ensure that the pacemaker is not making mistakes and the heart model is correct? All right, so I think we are a bit over time, so let me stop here, and if you have questions, let me know.